So essentially, what is a donut? A donut takes the shape of a torus in which there's a circle that revolves around a central axis. Here we can break down the radii of the torus. We can do this by assigning two radii. One extends from here to here. We'll call this little r. The other extends from the center to the edge. We'll call this big R. So if you imagine a torus, let's say we make a cut right here where the little r is. If we take this edge and put it over here and take the bottom edge and put it over here, we essentially got a cylinder. But if we draw this sideways, we can visualize it like this. Now, we can see that it forms a cylinder in which we curve it to make it look like a torus. To find the volume of any prism, what we can do is we can find the area of the base and multiply it by the length, which we'll describe as L. So now we know that the base of any circle is going to be equal to pi r squared, because we can see that the base of a cylinder forms a circle. Now we need to multiply this by the height, or length in this case, which is L. If we look really carefully, we can see that L is actually equal to the circumference of this torus, which can be seen as this line. And since it kind of forms a circle, we can tell that the circumference is going to equal to 2 pi r. In this case, we're going to use big R because it extends from the center of the circle. So now we have the area of the base, and now we have L. So now we can just multiply these two terms together, which then results in pi r squared, which is equal to the area of the base, times the whole entire length, which can be described as either this or as this, which is equal to 2 pi r. And this gives us the volume.
So now that we have the volume of a 3D torus, the problem is that we want to find the volume of a 4D torus. Now a 4D torus is a fourth dimensional donut essentially. But what even is the fourth dimension? To figure out, let's start by talking about the third dimension. So right now we live in the third dimension, and as you notice, there are three axes of movement. There is the y-axis, which is up and down, the x-axis, which is side to side, and we also have a z-axis, which is forward and backwards. Now if we want to go to the fourth dimension, we have to add another axis of movement. So to do this, we will add another axis and call this W. Now this axis of movement is really hard to understand in 3 dimensions because we only have left, right, up, down, forward, and back. But just imagine that we live in a fourth dimensional world where we have left, right, up, down, forward, back, and a movement in another plane. And that is essentially what the fourth dimension is. So now, we want to turn a 3D torus like this one, except more perfect, into a fourth dimensional torus. So here we have the 3D torus, and it is essentially just a donut. Now how do we turn this into the 4D torus? So if you recall, with a 3D torus, what we did is we took a circle and we revolved it around some axis. So if you pretend that we have an axis here, we took the circle and we revolved it around it. So imagine that the circle is moving like this through the axis of revolution, and you get a donut. Now in a 4D torus, instead of starting with a 2D circle and creating a 3D torus, you start with a 3D torus, and you want to end up with a 4D torus. So to do that, you create another axis of revolution, and you make the torus revolve around that axis of revolution. Now this can't be done in 3 dimensions because there's just simply not enough space. It's as if I'm trying to put an infinite amount of toruses squished together and pulling them out into another torus. But that can't happen in 3 dimensions because they're simply overlapping. So in order to do that, in order to have enough space for both toruses, or tori, I need to go into the 4th dimension, and now I can create a 4D torus, which in this case, this type of 4D torus is called a it's called a ditorus. So now we want to figure out what the volume of this ditorus is. So in order to do that, we can break apart the ditorus. If you notice, if we similarly cut this along here, as we did with the regular torus, we can stretch this out into what seems to almost be a cylinder, but instead of being a cylinder, it has the base of a torus. So it has the base of a 3D torus that's extruded along a path. And this is what's called a 4D torrender. Now, if we can find the volume of this 4D torrender, we essentially have the volume of this 4D ditorus. So in order to do that, let's label some variables. Similar to the other torus, this will be little r. From the center all the way to the edge will be big R. And if you notice, we also have a smaller torus right here. And we need to label that too. So the value of the smaller, or the minor radius of the ditorus will be what we call P. So now we know that we want to figure out what the volume of this 4D torrender is. So this is essentially a 4D prism. And if you remember with the cylinder, a prism's volume will be equal to the volume of the base times the length. So we already know what the volume of the torrender is. So we know that the volume of the torrender is pi r squared times 2 pi r. But in this case, the r is going to be switched with p because we're using a smaller torus, and the big R will be switched with that r. So that's the volume of this smaller torus. So now that we have the volume of just the base, we want to find the length of the torrender. So we want to find this value. And if you remember, similar to how we figured out the length of the cylinder in the 3D torus, we can use a similar process to figure out the length of the 4D torrender in the 4D ditorus. So this length is essentially going to be equal to the circumference of the entire ditorus, because this is just an unwrapping of the ditorus. Therefore, the circumference of this is going to be 2 pi r, big R. So we know that the length will be 2 pi r, and therefore the volume is going to be equal to everything multiplied together or pi, or 4 pi cubed times p squared times r times big R. And that is your 4D volume of the ditorus. So this is the problem about 4D donuts that we have to solve. So let's see how we would solve it. So we start with a 3D donut. So immediately we know that we can draw, as we discussed earlier, a 3D torus that looks something like that. And that's with a little bit of shading to show it's 3D. So that's essentially a 3D donut. Now the 3D donut is being prepared with a minor radius of 3 centimeters and a major radius of 4 centimeters. So we talked about what a minor radius and major radius was before. The minor radius would be this value, and we can assign this as, you can't really read that, we can assign this as p, little p, lowercase p. And the major radius will be the radius of the entire donut, and we will call this value lowercase r. So now it tells us that some special dimension dough is added to the donut along the 4th dimension to form a 4D ditorus, which is essentially that this donut has been expanded along the 4th dimension to turn into a 4D ditorus. So now the chef puts this in the oven, and you notice that the ditorus begins to expand as it bakes. You notice that the minor and major radii of the base donut stays in the same proportion. So that means that the ratio of P to R will always stay the same. Or actually, first, we should note that P equals 3 centimeters and R also equals 4 centimeters. And since P and R will stay in the same proportion as the donut expands, we can say that the ratio of P to R will be equal to 3 centimeters over 4 centimeters, or 3 over 4. So now we also know that the major radius of the base donut, which is this is the base donut, since the base donut of a ditorus is a 3D donut, is growing by 1 centimeter per second. So we can say that dr over dt is going to equal 1 centimeter per second. Now you also notice that the entire ditorus's radius is growing at a 0.5 centimeter per second. So the entire ditorus's radius would be from this to here, which we will label big R. So now we know, so I'll remove or erase a little bit of this so I have a little bit more space. But so we know that the change in the large radius over the change with respect to time is going to be 0.5 centimeter per second. Now the problem goes on to saying that the donut will be half-baked when the 4-dimensional volume, which was here but I erased it, is 9 pi centimeters to the 4th, and the radius of the entire ditorus is 4 centimeters. So that means that V will equal 9 pi centimeters to the 4th, and the radius of the entire ditorus, which is R, will equal 4 centimeters. And you want to know how fast is the volume increasing when the donut is half-baked. So you want to find the change in volume with respect to time. So now we can use these values to solve for the volume of the 4D donut as it changes. So let's quickly review what we know so far. We know that the minor radius of the base donut, which is P, is equal to 3 centimeters, and that the major radius of the base donut is equal to 4 centimeters at the beginning. And we know that these two values stay in the same proportion. So we can say that as the ratio of P to R is going to be equal to 3 to 4. Now we also know that the change in the major radius of the base donut with respect to time is equal to 1 centimeter per second. And we also know that the change in the entire ditorus's radius with respect to time is equal to half a centimeter per second. Now we also given more information that when the torus is half-baked, we know that the volume is 9 pi centimeters to the fourth, and the entire radius is 4 centimeters. And we want to find the change in the volume with respect to time when the donut is half-baked. So essentially, what the change in volume is using these values. So in order to do this, we can use the volume that we discovered in the past, just a little bit before. We discovered that the four-dimensional volume of a ditorus is equal to 4 pi cubed p squared minor radius times major radius, or major radius times the entire ditorus's radius. So now, since we want to find dv over dt, why don't we try taking the derivative of this? So if we take the derivative of this, we get dv over dt is equal to 4 pi cubed times, now p squared, we actually have to use the chain rule since this is all a function of time. So we get 2p times the inside function of the change in p with respect to time times the change in the radius with respect to time times of the change in the major radius with respect to time. So now if we look at this, we can try and see what values we have and what values we don't know. So we know what dr over dt is. We know what the change in the major radius with respect to time is. We, however, don't know what we don't know what this is. And we don't know what the change in the minor radius of the base donut is, and we also don't know what the change in what the p value is at the instant that it's half baked. So how we can fix this is if we substitute in our ratio for p. So we can put this all in terms of little r and big R. Now basically we want to figure out a way to take the p variable out of this equation, and we can do that using the ratio. So if we do that, actually these should be dt and dt. If we use this ratio, we can see that if we multiply r across, we can see that p is equal to 3/4 r. So if we substitute that into the original equation, we can solve for the derivative for the change in the volume. So we get 4 pi cubed times, now we're substituting in p, so we have 3/4 r squared times r times big R, and you can multiply that throughout, and you get times 9/16 r cubed times big R. Now we take the derivative of both sides once again. So we have the change in velocity over the change in time is equal to, the derivative of this will be 4 pi cubed times 3 times 9/16 r squared times the rate of change of r times the rate of change of the big R. So now let's check and see what values we know here. We know dr over dt, big R, we know big R over dt. We also know the change of the smaller r over dt. However, we don't know what the major radius of the base donut will be when it is half-baked. As you can see, when it's half-baked, we only know these two values. So we don't know what this is. But using these two values, we can figure out what this r value will be. Okay, so now we want to find out what the major radius of the base donut's value will be, which is r, when it is half-baked. Because that is the instant that we are solving for. And using these values, we can figure out what that is. So let's plug in to let's get the original, the equation for the diameter. The equation for the four-dimensional volume, which as we know from before is 4 pi cubed p squared little r times big R. And now we only know what r is, and we know what the volume is. So we want to take out p essentially, and we can do that using this ratio that we have. So we substitute in that p will be 3/4 r squared times r times r. And now we want to figure out what this r value will be at the instant that it is half-baked. So in order to do that, we substitute in these values for v and major R, or big R. So we get that 9 pi centimeters to the fourth is equal to 4 pi cubed times 9 over 16 r cubed times 4 centimeters. So now we can isolate r cubed by saying that r cubed will be equal to, we divide by everything on this side, divided onto that side, so we get 9 pi centimeters to the fourth over 4 pi cubed times 9 over 16 times 4 centimeters. And if you plug that into your calculator, which I will do, you should get a value of about 0.101, which is approximate. So then you take the cube root of that value, to get the value of r, which is approximately 0.466 centimeters. And you notice that the cube root of centimeters cubed will be centimeters. So we know that our answer is at least in the correct units. So that is our value for r, which we can then plug into the derivative equation later to find the change in volume. Okay, so now we know that the major radius of the base donut, which we represent with lowercase r, is equal to 0.466 centimeters when the die torus is half-baked. So now we want to find the change in volume with respect to time at the moment when it is half-baked of the die torus. So we can start off using the volume formula that we calculated earlier. So we know the 4D volume of a die torus is 4 pi cubed times p squared times lowercase r times capital R. So now we want to try and get rid of some of the variables and try and simplify this. And we can see that we can put P in terms of R since we have this ratio which says that P over R is equal to 3/4, or P is equal to 3/4 R. So we can substitute that in for P, and we get that that volume is equal to 4 pi cubed times 3/4 R squared times R times capital R. And now we can simplify this by multiplying by squaring the inside. So we get 4 pi cubed times 9 over 16 R squared times R, times R times capital R. And we can simplify that even further by saying that we can see that the 4 and the 16 can be divided out, so we get 9 over 4 pi cubed. And now R squared times R, these are the same variable, so it just becomes R cubed times capital R. So now that we have this equation for the volume, we can start taking the derivative of this, because if we take the derivative of this, we will get the change in volume with respect to time, which is what we're looking for. So we say that that the change in volume with respect to time is equal to, this is a coefficient, so it can, when you take the derivative, the coefficient stays the same. And now you're going to multiply that by, we see that we have two different variables multiplied against each other. And when we want to take the derivative of this, we have to use the product rule. So the product rule says that if I have f of x, and that equals two terms multiplied with each other, we'll call them g of x and h of x. If I want to take the derivative of f of x, it is equal to the derivative of g of x times h of x plus g of x times the derivative of h of x. So if we do that with this, we can see that the derivative of r cubed will be 3r squared using the power rule. And then we also want it with respect to time. So we can assume that r is a function of time, and if we use the chain rule, we know that we have to multiply this by the derivative of r with respect to time, and then we also have to multiply that by h of x, which is just, in this case, is just capital R. And then we add that to r cubed, to r cubed times the derivative of this, which in this case is just d capital R over dt. So now we can plug in variables. So we have that the change in volume with respect to time is equal to 9 over 4 pi cubed times 3. So now we look for R, and we know that R, when at the instant that it is half-baked, will be 0.466 centimeters. 66 centimeters. And you have to square that, multiplied by dr over dt, which is 1 centimeter per second, times R, which when it's half baked will be 4 centimeters, and we add that to r cubed, which will be 0.466 centimeters cubed, and we multiply that by the change in the entire ditorus's radius, which is half a centimeter per second. So if you plug that, you should get that the derivative, or the change in volume with respect to time, is equal to 185.33. And let's check the units really quick. So we have, over here you can see that we have centimeters squared. So I'll write that over here. We have centimeters squared times the centimeters from here, times centimeters, times the centimeters from here, centimeters, and that is actually over a second, so that will equal centimeters cubed per second, and you add it to centimeters cubed times centimeters per second, which, as you can see, ultimately just you get the units of centimeters to the fourth per second. So that means that the final change in volume with respect to time will have the units of centimeters to the fourth per second, which makes sense since this is four-dimensional volume. So if you have third-dimensional volume, it's just centimeters cubed. But in four-dimensional volume, it's centimeters to the fourth, and then it's per second because it's a change in time. So your final answer is that when the ditorus is half-baked, at the instant that it is half-baked, the change in the change in volume with respect to time will be 185.33 centimeters to the fourth per second.